In this video, I'll be going through a couple of extra solution stoichiometry problems. I'll be going through one traditional and one titration, and I'll actually be doing a redox titration just to show you that the titration that you do doesn't have to be acid-base. Any kind of titration can be solved using the titration equation. So I start with this one here. This one we've got a complete balanced chemical equation between zinc and hydrochloric acid, and we're asked to calculate the volume of 4.33 molar hydrochloric acid that is needed to react with 7.88 grams of zinc. So the approach that we're going to take here is really familiar. It should be really simple for us to do. We have our starting mass of zinc. We're going to turn that mass using molar mass to figure out the number of moles of zinc. We're going to convert that number of moles of zinc to moles of hydrochloric acid using the balanced chemical equation. And then we're going to turn that number of moles of zinc or hydrochloric acid into liters or milliliters of hydrochloric acid. And so along the way, we're going to use some tools that we should already know how to use. Molar mass will be used to do that first step. Balanced equation will be used for the second step. And then molarity will be used for the third step. And as I showed you in the previous video, these can all be done using dimensional analysis techniques, even the molarity, because if we understand our definition of molarity, molarity is equal to moles of solute, which in this case would be hydrochloric acid, divided by liters of solution. Well, right there you have a definition. Right there you have a fraction, a conversion. And so we can turn this 4.33 molar HCl into 4.33 moles of HCl divided by 1 liter of HCl solution. And that can be our conversion factor. We just have to apply it the correct way. So starting off with our dimensional analysis, 7.88 grams of zinc, I know that for every 1 mole of zinc, I would get 65.41 grams of zinc. That is my molar mass. And so there we have it. I've got my first conversion in. Second, I need to convert the moles of zinc to moles of HCl for the balance equation. 1 mole of zinc converts 2 moles of HCl. So I've got that one now set up. And then finally, now I can use my balanced, or my molarity, 4.33 moles of HCl for every 1 liter of HCl solution. And so that last one goes in there. Set up my calculation, get my calculator out here. And while that's going, make sure that everything cancels out that needs to cancel out. So my grams of zinc are canceled out there. My moles of zinc are canceled out there. My moles of hydrochloric acid are canceled out there. And I'm going to be left with liters of solution at the end of this, which is a volume, something I can use. 7.88 multiplied by 2 divided by 65.41 and divided by 4.33, I get an answer of 3 significant figures, 0.0556 liters. Now, more often than not, we would probably view this as being kind of a smallish number. So converting it to milliliters is not that difficult. We would get 55.6 milliliters of HCl solution as a result. So depending upon what you need, sometimes this is enough. In our previous example, it was. Here it's a little bit small, so multiplying by 1,000 gives us a number that we can actually measure. And so we could take a graduated cylinder and measure 55.6 milliliters of that solution to get it to react with all of that zinc. So again, when it comes to doing solution stoichiometry, follow the same kind of process that you had in other kinds of stoichiometry. Figure out what steps you need to do and then how you're going to go about doing those steps. Now, in our second example here, we have a redox reaction. Permanganate is reacting with iron 2 ion to make manganese 2 ion and iron 3 ion. And we see that we've got everything balanced up here already. The question is, determine the concentration of a potassium permanganate solution if 13.99 milliliters of 0.115 molar iron 2 chloride solution is required to completely react with 20 milliliters of the potassium permanganate solution. Now, when you see problems like these, what I want you to think about and remember is that these equations always are net ionic. And so what we want to do is we want to see what are the net ions in the reactants and how do they relate to what is in our equation. So we can see that the potassium permanganate contains permanganate ion and that it's a 1-to-1 ratio of potassium permanganate to permanganate ion. So whatever we determine the concentration of this stuff to be, it'll be the same as the concentration of this stuff and vice versa. The other task that we can look at is we can see that we've got iron 2 chloride, which contains iron 2. And so that's going to directly correlate to this. And we can see that this is also a 1-to-1 ratio of iron 2 chloride to iron 2 plus. And so whatever we determine the concentration of this to be, it'll be the same as this and vice versa. So since I have a balanced chemical equation and I've got essentially a titration here, I've got volumetric amounts of two different solutions. And so even if I don't break out all the glassware and the burettes and everything, I'm still looking at a titration here because I'm doing a conversion from one solution to another solution. And so if that's the case, the titration equation qualifies. Molarity of 1 times the volume of 1 over the coefficient for 1 is equal to molarity times volume divided by the coefficient for the second item. And so if I have both of these, and they're both ratios, they're both fractions, I can start plugging in values. I'm just going to use potassium permanganate is going to be my 1, iron chloride is going to be my 2, and I can plug these in and have it make complete sense to me. So I don't know what M1 is, but I know that I had 20.00 milliliters of that solution. Divided by its stoichiometric coefficient, which was 1. And I know that that is equal to the data here for the iron, 0.115 molar times 13.99 milliliters. And the coefficient on the iron is 5. It's a 5-to-1 ratio. Well, if I figure all this out the rest of the way, what I'm going to have is the calculation on this side is going to yield 0.115 multiplied by 13.99 and divided by 5. So I get, on this side of the equation, 0.322 molar times milliliters. And on this side of the equation, I have M1 times 20 milliliters still. If I divide each side by that 20.00 milliliters, then my 20 milliliters cancel on the left side, just my milliliters cancel on the right side. I end up with the molarity for solution 1 is 0.322 divided by 20, and I get a concentration there of 0.0161. Potassium permanganate as the concentration of the solution. Now you could solve this with solution stoichiometry. You could have converted this into moles and then done a conversion to find the number of moles of potassium permanganate and divided it by the 20 milliliters, and you would have gotten a molarity. And in fact, I will show you what that looks like here in the margin. So you could have done it stoichiometrically using this process. You start with your volume of iron chloride. You use the molarity to turn the liters into moles, and then you use the mole to mole ratio to figure out the number of moles of potassium permanganate, and then take the number of moles of potassium permanganate, divide it by the volume, and if you do that, divided by 0.02, you get to 3 significant figures, 0.0161, the exact same concentration that you got through a much simpler process using the titration equation. So the point I'm getting to here is that if we're doing any kind of calculation involving conversion of one solution in concentration to another solution in concentration, even if it's not formally a titration, even if it's not acid or base, this will work in any kind of circumstance, and it's a real time saver to use this equation, but you have to use it correctly, meaning you have to use the denominator here and get the correct coefficients from the balanced equation. Without that, this is just a dilution problem, and dilution problems are not always accurate. It implies that it's a 1-to-1 ratio of the two things that you're comparing, which isn't always the case. I'm going to put some extra videos, other YouTube videos that I like, that will give you more practice here in the links in the bottom and in the description. But until then, have a good day.